Hi, this is Gin Sheh. This video is for the homework 10 number 2 question. In the number 2 question, there are about 8 sub-questions. So we combine all of them into this video. The first question of the number 2 is white sands stationary process, which called WSS. The first property is eta of t is the constant value. Second, constant value not including the zero. Second is autocorrelation R of T1, T2. R of T1, T2 equal to R of T1 minus T2. Only depends on this one. Only depends on this one. If this T1, if this is not T1 minus T2, it will not be the white sands stationary. Here, the third property, actually it is not a property, but it is some kind of examples, like which is Poisson increment process, Poisson impulse process, and random telegraph signal belong to the white sands stationary. On the other hand, the Poisson process, a semi-telegraph signal, and the random walk and the Wiener process are not belong to white sands stationary. The fourth, the property D, x of t is SSS. The SSS is strict sense stationary, and the expected value E of x squared of t exists, and x of t is white sands stationary. So note. For example, the Canch distribution process, as f of x equal to alpha over pi multiplied by 1 over alpha squared plus x squared. The expected value x power of gamma of t doesn't exist for any gamma. So this one, the Canch distribution process is not belong to the white sands stationary. The property E, x of t is a strict sense stationary. If the x of t is white sands stationary. Actually, it is not generally true, because white sands stationary involves only the first and second orders moments. So, if the x of t, SSS of x of t in the first and second order equal to the white sands WSS first and second order, and it will be the WSS. But if for the third order, then x of t will not be the WSS. Property F, x of t is normal and white sands stationary when the x of t is SSS. This is for the white sands stationary. Okay, then I'm going to continue the Markov. The Markov process. The past x of t is not influenced on the statistics of the future x of t under the condition. The condition here means condition probability that the present is none. This is a tight domain, so then I can make example on this one. So this is now T2 is now, and this is a past Tn, and this is for the future T1. So all the value smaller than T2, I mean here T3, T4, T5, T6, T7, whatever is greater than T2, will not influence the future. So there we call the Markov process. So this is example. Probability of f of x t1 small and greater than x of t1 in condition of x of t2, x of t3, x of t4, and go on. So because t2 is the present value, so T3, T4 is the past value, so we don't need to care about the T3 and T2, so we can just ignore this one. So the new probability condition probability will be probability x of T1 under the condition x of T2. A Markov process is statistically determined, but if one knows its second order distribution function f of x1, x2, t1, t2. So in this one we have a small definition and explanation here. So if x1, x2 to the xn is a general sequence of the random variable, then it is statistically determined by its nth order probability masses. So this is one. Probability of x1 is to the xn for any n. The second one, if x1, x2 is a Markov process, or we can call Markov chain, and it is statistically determined by its second order property masses. So this is and then we need to prove this one. What is the second order here? Because okay, this is the n from 1, 2, 3, 4 to the n, and then there's a probability, and it is determined by the second order, which is only the only its second one. For example, x1, x2, and only determined by the x1, and x2, x3 only determined by the x2, x3, x4 is determined by the x3. That's the second order. So here we can rewrite this whole thing as the probability xi equal to xi, and there's a summation from k from minus infinity to the infinity, and then probability xi equal to xi, xj equal to k, So here we can see here only that's the second order. Okay, that's conditional. So let's determine the next one, which called the second order. The third one, if x1, x2 is the sequence of an independent random variable, then it is statistically determined by the first order probability massive. So the first order, now we talk about the first order. So probability xi equal to xi for any I equal to 1, 2, 3, 4. So that determined by itself. Okay, the first order. Example, for the Poisson process, semi-random telegraph signal, random telegraph signal, random walk, and the Wiener process are Markov process. Okay, the next one is normal process, which called the Gaussian. A process x of t is said to be the normal if the random variable x of t1, x of t2, x of tn are joined normal for any n, for any t1, t2 to any tn. So this is the formula. Example, x of t is given by the x of t equal to a cosine omega t plus b sine omega t. The a and b are two independent normal random variable. So expect value a equal to expect value b equal to 0. On the other hand, it's expect value of a squared equal to expect value of b squared equal to the this square. In here, omega is a constant. And then we need to find a second order density function. So the answer is the random variable x of ti are linear combinations of the normal random variable a and b, and the a and b are the joint normal. That's a condition we talk here. Because a and b are joint normal, so yj of dj x1 and okay, I should when AB are joint normal, so the yi are the joint normal. The autocorrelation value, this is the autocorrelation value. This sigma. Okay, autocorrelation value R of T1, T2, it will be equal to expect value A cosine omega T1 plus B sine omega T1 multiplied by A cosine omega T2 plus B sine omega T2, and they will become sigma cosine omega T1 minus T2. So we can assume the T1 minus T2 as a tau. So, and covariance covariance value will become this one. Okay, that's what I thought. Okay, strict sense stationary process called the SSS. If the statistics is not affected by a shift on the time axis, okay, it means on the time axis, no matter how you change, and the value, the statics remain itself, and then this means strict sense stationary. So that's coming. On the other hand, the two process t x of t and x of t plus var epsilon have the same statistics for any var epsilon. Now this is a condition, this definition. X of t is the strict sense stationary if only if f of x, fx of x1, x2 to the xn, t1, t2 to the tn is equal to the t is equal to fx t1, t2 to tn, t1 plus var epsilon, t2 plus var epsilon to the tn plus var epsilon for any n and any t1, t2 to tn and any var epsilon. Okay, it means this can be swapped and the values remain its value. Example, any IID system, independent identical distribution random variable is a strict sense stationary process. B, x of t is SS when the f of xt equal to f of x. The third one, C, x of t is SS when the expected value of x of t equal to the eta equal to the constant if the eta exists. Okay, it means not zero. D, x of t is SS when the f of x1, x2, t1, t2 equal to fx t1, fx1, fx2, t1, t2. Let's separate this a little bit different. X of t is SS when the autocorrelation R t1 t2 equal to R t1 minus t2, and if the expected value x squared of t exists. Okay, I think that's all my answer. Thank you.